Hi everyone, my name is Justin Chun and I'm from the KGSEA Math Circle, and specifically I'll be talking about two key mathematical concepts that have influenced music theory. The first one is Pythagoras' discoveries about harmony, and the second is Fourier series. These two concepts help us understand the structure of sound and are tools that shape how we compose, understand, and even experience music. Starting with Pythagoras, a Greek mathematician and philosopher from around 500 BCE, while many of us know him for the Pythagorean theorem in geometry, his contributions to music theory were just as groundbreaking. Pythagoras believed that numbers were the essence of the universe, and through his experiments with sound, he discovered a profound relationship between numbers and musical harmony. Pythagoras' experiments involved vibrating strings. He found that the pitch a string produces is directly related to its length. When you pluck a string, it vibrates to create sound waves, and the length of that string determines the frequency or pitch of the sound. More importantly, Pythagoras discovered that when the lengths of two strings are in simple ratios, such as 2:1, 3:2, or 4:3, the resulting notes sound harmonious together. These ratios form the basis of octaves, fifths, and fourths in music, and they are still fundamental to Western music theory today. For example, the ratio 2:1 corresponds to an octave, the simplest and most consonant interval in music. If you have a string that is, say, 1 meter long, and you shorten it to 0.5 meters, the pitch will rise by 1 octave. The ratio 3:2 corresponds to a perfect fifth, another pleasing interval that forms the basis of many harmonic progressions in music. Pythagoras called this the music of spheres, believing that these harmonious relationships could explain not only music, but also the structure of cosmos. These simple ratios form the core of Pythagorean tuning, an early system for tuning musical instruments. In this system, each note's frequency is determined by these basic whole number ratios. While modern tuning systems like equal temperaments have evolved to accommodate more complex music, the principles of Pythagoras still provides the foundational logic for how we think about intervals, scales, and harmony. Moving on to another mathematical concept that has deeply influenced our understanding of music is the Fourier series, named after French mathematician Jean-Baptiste Joseph Fourier. The Fourier series breaks down complex waves like the ones created by musical notes into simpler sine and cosine waves. Essentially, Fourier showed that any periodic wave, like a musical sound, can be represented as the sum of multiple sine waves or of different frequencies, amplitudes, and phases. So why is it important in music? Well, when you play a musical note, you're not hearing just one pure note. You're hearing a combination of tones known as harmonics and overtones. The fundamental frequency is the pitch you perceive, but there are other frequencies layered on top, creating the timbre or tone color of the sound. This is why a note played on a piano sounds different from the same note played on a guitar. Even though the pitch is same, their harmonic structure is different. The Fourier series gives us a mathematical framework to understand this. By breaking down a sound wave into its component sine waves, we can analyze the harmonic structure of a note. For example, if you play an A4 note on a piano, which has a fundamental frequency of 440 Hz, it's not just one frequency you're hearing. Fourier analysis reveals that there are harmonics at 880 Hz, 1320 Hz, and so on, each one an integer multiple of the fundamental frequency. These harmonics blend together to create the rich, full sound of the piano. Delving deeper into the mathematical formula behind the Fourier series, for function fx that repeats over a period of L, the Fourier series is written as provided. When an and bn are Fourier coefficients, which determine the amplitude of each sine and cosine waves, these coefficients are calculated by integrating the function over one period. Musically, this means that every sound you hear is actually a complex combination of simpler sine and cosine waves, and Fourier analysis helps us understand and manipulate those combinations. The Fourier series is also used in audio engineering. For example, when you use an equalizer to adjust the bass and treble in a song, what you're really doing is manipulating the amplitude of specific frequency bands, which is only possible because of Fourier series. This concept also underlies compression algorithms like MP3 and AAC, which reduce the size of audio files by eliminating frequencies that are less perceptible to the human ear, known as amplification of Fourier's transforms. So the works of Pythagoras and Fourier Fourier shows us that music is much more than an art form. Its interaction with sound is directed by mathematical precepts, and Pythagoras gave us a basis from which to understand harmony through simple ratios, while Fourier gave us means to analyze and synthesize sound by wave decomposition. These two findings set up our perception of music today, either through acoustic instruments or through digital synthesizers. I really do hope that all of you found an interest to further continue learning about the various relationships in mathematics. Thank you for listening.